For our second example that we'll look at for optimization problems, it says, suppose you have 20 feet of wire and want to make an equilateral triangle and a square. Now you're allowed to make only one of them. Yes, you can make both or just only one of them. How much should be used for each if we want to maximize the total enclosed area from both shapes? Okay, so if you remember from our first video, the very first step that we would like to do is draw ourselves a picture. So in this case, the pictures that make sense is first I will draw an equilateral triangle and I will draw a square. So again, after draw pictures, we should label some things with variables. So let's label the side of our equilateral triangles as x, and let's label the sides of our square as y. Now, as we saw in our first video, once we have this, then we'd like to create some equations. So what we'd like to do is we'd like to maximize something. So our goal here is to maximize the area. So we should create a formula for area. So our area in this case is we'll find the area of the equilateral triangle. Now the area of the equilateral triangle, you could throw down a little vertical piece there, use some special triangles. So the area that you're going to get is the square root of 3 over 2 times x times 1/2 times x. Okay, so to talk through this, what we have is the area of a triangle is always 1/2. So we have our 1/2 times the base. Our base in this case is the square, or is x. You see, that's our little x. And the height is the square root of 3 over 2 divided by x. You could use special 60, 90, or 60, 30, 90 right triangles. However you get this, use a equals 1/2. AB, sine, C, all of those types of things. Okay, so that's the area of our equilateral triangle. Then we have the area of our square. This one's just length times height, so it just becomes y squared. Now, as we saw on the first video, we have two variables. We'd like to be able to only have one, so we introduced what our constraint would be. Our constraint equation, this is the fact that we only have 20 feet of wire available. So 20 feet will be able to make the shape of our triangle as well as the shape of our square. So we could make the 3 sides of our triangle as well as the 4 sides of our square. Now we use this constraint and we're going to solve for one of the variables. Easier variable I'm going to solve for might be y, so we will solve for y to get 20 minus 3x is equal to 4y, so y is equal to 20 minus 3x divided by 4. Now we take this and we're going to substitute it into our area formula. So now our area formula is only in terms of x. And so if I multiply this first piece together, I get the square root of 3 over 4 times x squared plus 20 minus 3x divided by 4, that quantity squared. So now that we have the formula, or now that we have the area formula, our goal is to try to maximize this formula. And so again, we're looking for absolute maximums, not relative maximums. So if we can create the closed interval that makes sense, create this feasible region, then that will make this very easy. So we'll take a look at what our feasible region might be. So we say, what is the smallest that x is allowed to be? Well, in this case, the smallest would be x would be 0 because we'd use all of our wire for the square. So that would be 0. And then the largest it would be is if we used all of the wire for the triangle and none of the wire for the square. So since we have 3 sides of that and we have a total amount of 20, we would get 20 divided by 3. You could also just solve this constraint equation for y is equal to 0, solve for x. Okay, so now we have our feasible region. Now we would like to move on and we'll take some derivatives because our goal is to figure out what are the critical values in this feasible region. So if we take the derivative of this function, the derivative of the square root of 3 over 4 times x squared, we use our power rule, we get the square root of 3 divided by 2 times x. Now the derivative of this guy, we have to use our chain rule, so we bring down the 2. We will rewrite the inside as 20 minus 3x divided by 4, subtract 1 from the power, so that's just at the first power, and then we multiply now by the derivative of the inside. So the derivative of the inside, you could see this is 20 divided by 4, which would be 5, minus 3/4 x, so the derivative will be a negative 3/4. So if we simplify this, we get the derivative is a square root of 3 divided by 2x minus, we can have the 2 cancel with one of these 4s and be able to multiply this by negative 3/4, and then we would be left with a negative 3/8 times 20 minus 3x, which then could simplify to being the square root of 3 divided by 2x minus 15 over 2 plus 9x over 8, which again, we could just combine our like terms, find common denominators for the x's, and we would get 4 square root of 3 plus 9 divided by 8. This is the coefficient of x minus 15 over 2. Okay, so now that we have our derivative, we'd like to find our critical values. So we see, where is our derivative not defined? Well, it's defined for all values of x. So now we set this equal to 0. So we're going to look at 0 is equal to 4 times the square root of 3 plus 9 divided by 8 times x minus 15 divided by 2. We solve this for x, we'll have 15 divided by 2 is equal to 4 times square root of 3 plus 9 divided by 8 times x. Multiply the reciprocal over, simplify, and we're going to get 60 divided by 4 times the square root of 3 plus 9 is equal to x. Now, we'll keep the exact value for getting exact numbers, but we see, just as an approximation, this is going to be about 3.77. Now, it's good to check that because that is still in our feasible region. 20 divided by 3 is roughly 7, so we are good. So when we now found our critical value is this, we would now like to create that little chart where we have x and we have what is the area for each of these x values. So our first x that we're going to include will be our critical value of 60 divided by 4 times the square root of 3 plus 9. The next critical value we'll include will be one of our endpoints of 0, and then we'll include the other endpoint of 20 divided by 3. So we plug each of these into our area formula. So again, make sure you're plugging it back into the original one. Don't plug these into the derivative. So if we plug in this, I suggest just using a calculator, and what you would get is something that is about 10.7 or 10.87. We plug in 0 into this, we get a area of 25. And if we plug in 20 divided by 3, we get 19.25. So we see this is our largest area. So if we now try to make sense of what this is saying, we see that the maximum area is 25 square feet. And this occurs when, in this case, x is equal to 0. So that means is that we use none of our wire for the triangle and we use everything for the square. So this occurs when we do not include wire for the triangle and use all of the wire for the square. So there we go. Question asked how much should be used for each if we want to maximize the total enclosed area. We see that the maximum area is 25 square feet. We include all of the wire into the square, and so if you'd like to be more specific, what we see is that the dimension of the square, it would be a side length equal to 5 feet. And there we go. That is the second example.